This is a walkthrough of Exam 1 on 1 and 2-dimensional motion in Physics 131 for the fall 2021 semester. On the Autobahn, a guy in a Tesla has the autopilot set at 70 miles an hour. Motorcycle zips by at 110 miles an hour, constant speed. After a short delay, the guy in the Tesla decides to catch the motorcycle. He floors it, accelerates at a constant rate of 10 miles per hour per second until he flies by the motorcyclist, who is still going 110, at a speed of 160 miles per hour. In units of seconds, what is the time delay between the motorcycle passing the Tesla and the guy in the Tesla flooring it? That's the question. So let's start with a good diagram. There's the Tesla, there's the motorcycle. Tesla's going 70, motorcycle's going 110. Motorcycle goes 110 all the time. The motorcycle passes the Tesla remains at 70, and then the guy decides to catch up. And he accelerates at 10 miles per hour per second, and he reaches the motorcycle when the Tesla's going 160. So later on down the road, the motorcycle's still going 110, but now the Tesla's going 160. You have to really understand what's going on. We need the delay between the motorcycle passing the Tesla and the guy in the Tesla flooring it. That little time delay. So, after the guy in the Tesla floors it, it's going to take 9 seconds to get to 160 because he's going 70 now. He accelerates at 10 miles per hour every second. He's going to get to 160 in 9 seconds. So the total time is 9 seconds plus the time delay. The motorcycle's doing 110 the whole time. The average speed of the Tesla when the cruise is set at 70 is 70 miles an hour, obviously. The average speed when floored is the average of 70 and 160, and that's 115. The average speed of the motorcycle is always 110. We're investing this time to understand what's going on. The Tesla and the motorcycle are together when the motorcycle passes the Tesla, and they are together again when the Tesla passes the motorcycle. And we're looking for this time delay right here. Here's the speed of both of them. The motorcycle's 110 the whole time. The Tesla stays at 70 for some time and then accelerates to 160 at a constant rate of 10 miles per hour every second. So they're together here and they're together here. Clearly, the distance traveled is the same. We can calculate the distance each traveled. Relatively straightforward. The Tesla goes 70 miles an hour for some time. The distance is speed times time. Then it averages 115 miles an hour for 9 seconds. The motorcycle averages 110 the whole time, and that's the 9 seconds plus the delay. We have one equation and one unknown. This is all we have to do. We bring the 110 through, and we collect the T70 terms, and then we divide by 40, and we get the time, 1 1/8 seconds, 9/8 seconds. A little bit more than 1 second, and that's the answer. We can check it by calculating the distance. The motorcycle goes 110 miles an hour for 10.125 seconds, this is about a third of a mile. That's a perfectly legitimate unit of distance, 1113.75 miles per hour seconds. The Tesla goes 70 miles an hour for 1.125 seconds, averages 115 miles an hour for 9 seconds. We add those up and we get the same thing. That's problem 1. Problem 2. A sheer cliff, 75 meters high. The land above it is sloped at 30 degrees. At t equals 0, a large rock starts to slide some distance d up the incline, accelerates at 4 meters per second squared, reaches the edge in 5 seconds. Let's take these one at a time. What is the speed of the rock when it leaves the edge of the cliff? It accelerates 4 meters per second for 5 seconds. It's going 20 meters per second. That's easy, straightforward. Comes straight off, right there, at 20 meters per second. Part B, what's the distance d? Well, if it goes from rest to 20 meters per second, the average speed will be 10 meters per second. If it averages 10 meters every second for 5 seconds, it goes 50 meters. D is 50 meters. C, how far from the base of the cliff does the rock land? Okay, so now it's in the air. We need the horizontal and vertical components of the velocity of the rock when it leaves the cliff. So we have to get the angle of this velocity vector. Don't get this wrong. It's pretty straightforward. Take your time. Just draw a dashed line like this, and that has to be 30 degrees. Think about it. Invest some time doing that, getting it right. In the x direction, it's 20 meters per second cosine 30, 17.32 to the left. In the y direction, it's down 20 meters per second sine 30, which is minus 10 meters per second. We know what happens to these. The speed in the x direction doesn't change. The speed in the y direction increases by 10 meters per second each second. We can get the time of the flight from the y direction, the time the rock is in the air. In the vertical direction, we have y is equal to 1/2 at squared plus VIYT, and we know all of these but t. Goes down 75 meters. The acceleration is down 10 meters per second every second. The initial speed is 10 meters per second down. We can simplify this. We have 5, and we can divide by meters, multiply by seconds squared, and we get this. This is a quadratic. But we can factor it. T minus 3 seconds, t plus 5 seconds. Let's go back and see how that works. What the heck happened here? T squared, and then we have a 2, and we have a 15. So it looks like that's, remember this from algebra back in high school? This is -5 and plus 3. So -5, nope, +5, minus 3. That gives us the minus 15 when you multiply them, and the difference of +5 and minus 3 is plus 2. And if you want to check it, you can FOIL that out. T squared minus 3t plus 5t is plus 2t, and then minus 3 plus 5 is minus 15. So we neglect the negative solution. The time of flight is 3 seconds, and let's check that just to make sure. It leaves the cliff 10 meters per second downward, and it's in the air for 3 seconds. 3 seconds later, it's going 40 meters per second downward because gravity changes the speed by 10 meters per second each second in the vertical direction. The average of 40 and 10 is 25. You add them up, you get 50 meters per second. Divide by 2, 25 meters per second. If you travel 25 meters per second for 3 seconds, you go 75 meters, and that's the right distance. So that's all consistent. To get the distance from the base of the cliff, we use the horizontal direction. The rock goes 17.3 meters every second in the x direction. So after 3 seconds, it's going to go about 52. So that's part C. Part D, with what speed does the rock hit the ground? We need the components. In the horizontal direction, it's 17.32. In the vertical direction, it's 40 down. We can use the Pythagorean theorem, and we get 43.6 meters per second. That's D. E and F are plots. Plot the horizontal component of the speed. So that's the speed in the x direction. It accelerates this way, and then it hits the edge of the cliff, and that speed stays constant. In the vertical direction, it accelerates 10 meters per second downward in 5 seconds. It accelerates to 10 meters per second downward in 5 seconds. Then it accelerates downward at 10 meters per second every second to get to 40 in 3 seconds. So it goes from 0 to 10 in the vertical direction in 5 seconds, and then it goes from 10 to 40 in only 3 seconds. In the horizontal direction, the rock accelerates, I guess it's defined positive to the right, so it's negative. It accelerates in the negative direction to 17.32 in 5 seconds when it's on the slope, and then the speed's constant in free fall. So here are the graphs. This is the horizontal component. In 5 seconds, it gets up to 17.32, and once it leaves the cliff, it stays at 17.32 because gravity doesn't act in that direction. The vertical component, it goes from 0 to 10 down in 5 seconds, and then it accelerates at 10 meters per second every second. So it's at 10, 1 second later, it's at minus 20, 2 seconds later, at minus 30, hits the ground with -40 in the vertical direction. That's exam 1.